Yeah, like if I'd known that was the average, I probably just would have left it alone. With that, you're just mumbling. We're really to that. I just walked through the lab on the way in here. The password for today's, I shouldn't tell you the password for today's quiz. The password for today's quiz is funny. Yeah, it amused me. Knowing Dr. King as I do. There you go. Somebody won the lottery. Anyone in here win the Powerball? Because I would totally sell a grave for $1 billion. like, you know, I mean, people talk about ethics and all that. No, like if you find me a private island and I could just like walk away, yeah. Not selling a grave for $100 or something, but $1 billion, yeah, sure, okay. All right. So, yeah, I was 108. Somebody did very well. There were a handful of people that, like, basically, who was at the very top? I told you guys in class there were 4 people that essentially nailed the synthesis. So if you nail the synthesis, you're going to do way better than everybody else who didn't nail the 14-point problem. I have not looked at the syntheses you've turned in, right? None of these numbers include the 14 points that you turned in, extra credit. So the acid base is due today. Hopefully you've turned that in. I would probably take that late as long as it's in before I start looking at it this evening. So hopefully today we'll finish 21 and start 22. Need to get my note. Organized. You're a highly organized professor. All right. So like I said, we're in chapter 21. Enolates. Where was I last time? Figured out what I wanted to do with this. No, sorry, don't do that. That is still wrong. How can I do this problem wrong 18 times? It's be 100 degrees, it's going to be 70. All right, draw me a product for that. Keep an eye on protonation states. Which compound do you make the enolate out of? What functional group? Yep. Yeah, so if you were just gonna refer to that with words, what would you tell me that was? So an organic chemist would normally say the ketone. All right, so you can't say the ketone if there's two ketones, but if there's one, you can say the ketone, the other one would be the ester. We've talked about nomenclature in here some, and I'm not a huge, you can tell this, I'm not a huge fan of teaching nomenclature. So you guys all have access to ChemDraw. Seriously, the way organic chemists name compounds is to draw the compound in ChemDraw and ask ChemDraw what the name is. All right, that's the usual way of doing it. You need to know the basics. You need to know names of functional groups. You need to know that, you know, if we're going to number things, we're going to try to number them lowest. But conversing, nomenclature is important for conversing about molecules. So, you know, knowing the alpha carbon, knowing that's a carbonyl, knowing it's a ketone functional group is important. This is sort of like the benzaldehyde reaction, the aldol benzaldehyde, right? We only have, there's no enolizable proton on the ethyl benzoate. I wrote in here excess sort of at the end. Remember, we have this problem of which carbonyl gets attacked. We're not using a strong enough base to completely deprotonate the ketone. So the ketone could attack itself, right? You could, if we didn't have anything else here, you would have the alpha position here attack the neutral carbonyl carbon of another molecule. And that's still something that could happen. By using an excess of the ethyl benzoate, we like overwhelm that. There's more of that molecule for the enolate to react with. Even at the end, when there's only maybe a handful of ketone molecules left, there's still a lot of ester. And so, right, so the product, if you work through this, we're going to make an enolate here. This is going to be in equilibrium. Hopefully that acid-base worksheet helped you see these a little bit. Right on the top, we've got an acid and a base, conjugate base, conjugate acid. pK here is going to be in the ballpark of 19. pK here is about 16. Right, so the equilibrium does actually favor the top. Even though we want this reaction to go this way, the top is favored. And then I'm going to write, I think a lot of you know this abbreviation, but I haven't so far explicitly used it in this class, and I need to because I draw it all the time. A benzene ring like this, a mono-substituted benzene, is called a phenyl group. I can't say that. Whatever. The word, in terms of words, I'm limited in my words today, I guess. That comes from the German. So benzene is actually not called benzene in German. So that pH comes from that. All right, so the enolate's going to attack here. So that's what enolates do. Enolates are generally going to attack carbonyls. Enolates for single carbonyls are really only good nucleophiles for carbonyls. We'll talk about that a little more later in today's class. Just like any nucleophilic attack on an ester ever, you get a tetrahedral intermediate that's got a leaving group on it. This O minus, we kick ethoxide out. And so this kind of, well, actually, switch right here. Like without a proton source now, I'm having trouble managing my board. So now you get ethoxide. Over here, ethoxide is our starting base. So this is a base catalyzed process, except that it's not catalyzed. At the end, the last step here, we're going to get a deprotonation, give this more stable enolate. Right? Given what I've shown there, this would be the product. We're going to end up with an enolate as a product. And if we look at that, you can see also get ethanol out of this reaction. Get the pKa of ethanol, about 17. pKa of this proton is about 9. Right, it sits between two ketones. So each ketone makes that proton a little more acidic. 2 ketones is better than 1. 2 carbonyls is better than 1. And so the equilibrium really favoring the dicarbonyl enolate is what drives this whole process forward. Right, so the reaction sort of ripples along. Every left and right in any given step is sort of equally stable till the end when it falls off and becomes a low point. Obviously, at the end of this reaction, we probably wouldn't want to isolate this. We might, but we probably wouldn't. We would add some protons, some dilute acid. You know, often we'll work reactions up with a buffer like pH3 or something, enough to protonate that, but not to drive any other reactions. Questions? Yeah. Yeah, it doesn't have to be 78 degrees. In fact, this reaction will go at room temperature, but you can heat this up. Yeah. Do a second step. Draw what we get from that. So this is an orgo-1 reaction. So we have this enolate, we have this dicarbonyl enolate that is the conjugate base of a fairly decent acid. Right, so if that's a moderate acid, that's got to be only a moderate base. So the enolate, this enolate over here is the conjugate base of a weak acid, so it's a much stronger base. All right, and we have an alkyl bromide. And so the reaction here is just going to be an alkylation. If you saw that. But if you didn't, it's a new reaction. So these dicarbonyl enolates are really good SN2 nucleophiles. The product will be one, two, three, four. Put that alkyl group on the carbon between the 2 carbonyls. All right, so let's, did you get that at home? You didn't get that, sorry. I'll leave that whole thing on there for a minute. So some labels here. This is a strong base. This is a weaker base. That negative charge is stabilized by 2 carbonyls. So again, this elements of this came up in the acid-base worksheet.
how do you judge base stability? If you're judging base stability, if you know pKa's, you can look at the pKa's, right? So if you have an acid-base equilibrium, and you know the pK of the acid on the left and the acid on the right, you can just look at the pKa's. Like if you know that data, use that data. But for a lot of those, you might not have known the data. You might not have actually known what the pKa's were. You could look them up. There were pK tables laying around. But if you didn't, if you're going to compare the bases, right? So if you have an acid-base equilibrium, you're going to have an acid and a base on the left, conjugate acid and base on the right. Using pKa's means you compare the acid and the conjugate acid. Or you can use the bases and compare stability. So in fact, like you could compare, if we had an acid-base equilibrium between a monocarbonyl enolate and a dicarbonyl enolate, we'd be looking at the negative charge on the carbon, the lone pair on the carbon. How stable is that lone pair? Right? On the monocarbonyl enolate, we have one resonance structure. The lone pair is delocalized over 3 atoms, one of which is an oxygen. The dicarbonyl enolate, right, that lone pair is delocalized over 5 atoms, 2 of which are oxygen. So for the dicarbonyl enolate, that lone pair is more stable. That makes the molecule more stable. That means it would be favored at equilibrium. And so when you think about base stability, you have to look at not charge or generally sterics. You want to find the lone pair, the extra lone pair, and figure out where it's going to be more stable. Does that make sense? Okay, let's try another reaction. This is going to be called a malonic acid synthesis. There's a related acetoacetic ester synthesis. Sorry, guys. All right. So this is the overall process. And I'm going to walk you through. There's some sort of strange, there's some non-intuitive steps here. This is the overall process. Let me ask you, what would be wrong with this? You were going to, okay. So what I want you to do is look at the reaction I've just drawn up. 2 equivalents here means 2 molar equivalents, right? So we have 1 mole of acetic acid, we have 2 moles of LDA. So work through, this is a reaction that works a little bit. It's not a great reaction. So figure out, I guess what I'm saying is, this reaction in blue will give some of this product. Figure out the mechanism for that, 1 step. And then ask yourself why it's not a good reaction. When I say it's not a good reaction, I mean the yield is bad. And you can totally talk to each other. No better way to shut you guys up than telling you should talk to each other. There's no way to shut you to. Yeah, first thing is always draw the product at step 1.
Then I guess so. Because that's what we do. That would be the most acidic one. Then what you wanna put it all after. Oh, and then you could take it and change it to something. Like that. That's still- Is that how it looks?
Okay, I'm assuming we're taking a hydrogen off of here, but making it not good, because it's probably all the people from here.
Yeah, because if you do that, then there's like a whole thing here, which just doesn't make. I mean, I guess, or you could just.
I think that's, the issue, but I don't think we want to keep this hydrogen, and that's the problem. Like, I think we want to keep the hydrogen.
I've added a reaction in orange. Figure out the product of that. What if you only had one equivalent of LDA?
What's the flavor?
When I sit down with some time and a stable internet connection, you'll get to testify. It's soon. But probably not soon, like minutes soon, or even hours. Maybe tonight, maybe tomorrow. I'm trying not to whine about my life to you guys. I don't succeed at that very often, do I? All right, I'm going to start with the orange reaction. What happens if I add LDA to acetic acid? Takes which proton? Right. So LDA is a super strong base. Acetic acid is a pretty strong acid. Just because there's a disparity there, it's not like LDA is such a strong being such a strong base, it's going to do something weird. You have an acid, you have a base. What's a ballpark pKa for acetic acid? 4-ish, 3-ish. So we're going to get and right, so we'll get lithium acetate. What's pKa for a NH, an H on a neutral nitrogen?
9 to 11.
So this is a really common thing to think, and it's. I mean, I'm not sorry. You answered it, and I'm glad. I'm points for answering. Like not really imaginary. Sorry, but you guys. I mean, everyone should listen to this. All right, this is an error that will keep getting made. H on a nitrogen. By far, for most of you, the H's you're going to see on nitrogens are going to be H's on protonated nitrogen. Right, so an NH plus. The pK for those are around 9 to 10, 9 to 11. That is not an NH plus, it's a neutral nitrogen. Right, so it's a lot less acidic. pKa for this is about 38. pKa for this is, it is 4.5. So that is 33, 34 orders of magnitude difference. That means if we had like, what would that be? 10 to 30, 30. We had 10 billion moles of acetic acid. Be a lot of acetic acid. And we added 10 billion moles of LDA. It's a really stupid amount of LDA. We would have one acetic acid molecule somewhere in. So this equilibrium really favors the right by far. We say this goes to completion, right? Okay, so that's after one equivalent of LDA. So what do we get if we add one equivalent of LDA to this? Go ahead and work on that. You might already have it, in which case you can work on that. And just to go back and hammer this message, differentiate. You guys should, very important to differentiate these two things. Right, pKa over here, 9 to 11. pKa here is in the mid-30s. All right, very different things. And it's, I see it all the time. Like you guys stick NH in your mind, all NHs are the same, and it will lead to errors. All right, work on that second equivalent of LDA. So what is LDA again? It's a strong base. So do we have an acidic proton? Okay, we do. Yeah. LDA is a strong base. There's a methyl group there that's next to a carbonyl. The fact that there's already a negative charge on the molecule is going to make the the whole reason the carbonyl is making that CH more acidic is it's pulling electron density away from it. That carbonyl is already involved with some negative charge, with some excess electrons, it's going to be less free. But we all know people, you know, who have too much, you still want more. So this carbonyl is still electron withdrawing, and the result is LDA is going to pull that proton off, and we're going to end up with that enolate. And I'm going to draw it like that, so you get two negative charges on the opposite. The pKa of this proton with an O- on here is like 28. Right, but that's still more acidic, quite a bit more acidic than the conjugated acid of LDA. All right, so this is step 2. This is what we get, or sorry, step 1. This is our step 1 product in this blue reaction. I know I'm all over the board here. So we get this we get this dianion, and then we add butyl bromide. How does that get us where we want to go? Play with that for a minute. And also, remember that the actual goal we're driving at here is what's the problem with that, right? So you might see quickly how it works, but why is that a problem?
Like where? For that? Yeah, because I can say if we just can that's double bond. Where you go. Okay, yeah. And then. I see, because there's two of them. It's like, they're literally identical at this point. So like, obviously, but well, how does not work? Well, it doesn't matter which one. No. So that's, but then I'm saying, it's just saying that.
Really, pretty weak base, really weak acid. So, yeah. All right. So if you're looking at this, this is going to end up being an SN2 reaction. I'm just going to redraw butyl bromide over here. When you use an enolate as a nucleophile, you got to remake your carbonyl pivon, and then that would attack there. An SN2 reaction. So that's carbon. Let's number these now to try to keep track of. So 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And then if you want to go here, you've got to protein this. All right, so I haven't shown that stuff, but there's not an acid in there to protein that. The other thing I'd like you guys to get used to, well, there's two things I'd like you, there's a lot of things I'd like you to get used to. Okay. All right, but carboxylic acid, carboxylate, those are basically interchangeable. Right? If you have a carboxylate, all you got to do is acidify and you get the carboxylic acid. If you have a carboxylic acid, all you got to do is add a base and you get the carboxylate. You really need to keep track of, you know, what the pH is. Right? Is it acidic conditions, basic conditions? But those two, if you have a carboxylate, you also have a carboxylic acid. If you have a carboxylic acid, you also have a carboxylate. Right? All right. So what's wrong with this reaction?
The oxygens are super electronegative, so that carbon's not very good.
Actually, that carbon is really nucleophilic. So they are, the oxygens are electronegative. This is definitely how this nucleophile looks. One kind of minor problem is that the O, you can wind up alkylating the O's instead. So, right, instead of the carbon attacking, the O does. But that thing's right, it's the conjugate base of an acid that's got a pK of 28. So it's a really strong base. Which means it's going to be a good, it will be a good nucleophile if it acts as a nucleophile. But the being a strong base is the problem. So what reaction did you learn? It will do an E2, right? So when you learned SN2, somewhere right around that in time, you learned the E2 reaction. E2 is driven by a strong base. And probably, at least you're like most people, myself, right? SN2 and E2, the problem with learning that, neither of those reactions is all that difficult on its own. The problem is, you've got a compound that's got a leaving group, and you've got a molecule that's a base, but it's also a nucleophile. Like, how do you know which one that is? And I'm not saying SN2 by itself or E2 by itself are easy, but they're way easier than figuring out which is happening at a given time. In general, the stronger the base, the better the E2 reaction. So this is a very strong base. Therefore, E2 is a very likely reaction to have happened. So in general, enolates of single carbonyls, right? If you have an enolate with a single carbonyl, you've got a very good chance that you're going to do E2 rather than SN2. One of the ways around that, like you can always, if this alkyl halide can't do an elimination, right? So if there are no beta hydrogens, and if you think about that, like methyl iodide, there's only one carbon. You can't make a carbon-carbon double bond if there's not two carbons. But benzyl bromide, right? The beta carbon doesn't have any hydrogen. So any electrophile that can't do elimination, that works pretty well. So hence the need for this. Right, remember where this started. I drew this dicarbonyl compound and I said it's going to give us this. So I'm going to slide down the way and show you how that happens. Like I said, there's a few non-intuitive steps. So I think I'm just going to put it on the board and talk about it.
bless you. You can actually do this all in one pot. Right, I could take dimethyl malonate. You don't have to remember the name of this, but this is dimethyl malonate, hence malonic acid synthesis. If I treat with sodium methoxide, all right, so the product of step 1 is going to be to make an enolate there. Right, so methoxide is a strong base. The dicarbonyl compound is a pretty strong acid. Methoxide takes that proton, I get a nice stable anion. Now the whole point of this is, right over here, the enolate that I really need to make the molecule I want is a super strong base. This molecule is a much weaker base. I don't know if you guys remember this. I actually talked about this, right? So talk about looking at the stability of this negative charge. Right? A negative charge, the lone pair in a single carbonyl enolate, delocalized over 3 atoms, one's an oxygen. That's a stronger base than where it's delocalized over 5 atoms, 2 of which are oxygen. So this is the product of step 1. All right, you can probably see what's happening next. Then we put in our alkyl bromide, and obviously this could be any molecule that can do. It could be any molecule that can be an SN2 electrophile. Right, so it can't be a tertiary halide. It's got to have a leaving group for an SN2 reaction. Faster, the smaller that the alkyl group is. But you know, primary alkyl bromide is a good electrophile. So this is the product of step 2. So that is kind of a new twist on chemistry you've seen. Going from that product to the final product is completely new. Well, actually, it's not. There are 2 things that happen in step 3, one of which you've seen. So imagine that we walked in here today and I didn't talk, I didn't make any bad jokes. I just drew this. I just drew this blue molecule diester, H3O plus and H2O. What would you say the product of that was? Think about it for a minute. Draw the product out. What product would you draw out for taking that diester, treating it with aqueous acid, and heating it up? Remember the name of the reaction I'm looking for? What do we call a reaction in water that breaks bonds? Hydrolysis. Right. So what I would expect you guys to say here would be this. I would expect you to hydrolyze the 2 methyl esters. And I'm giving you like 2 minutes with me staring at you. Maybe that's not ideal, but I would expect you to come up with that. All right, aqueous acid, the esters, you're going to hydrolyze those to carboxylic acid. Right, so I think it's fair to ask you guys to know that. Going from there to the product, this requires only heat. So if you take a dicarboxylic acid like that and heat it up, we lose carbon dioxide. And we get, and if you count the carbons here, and I hope I've been drawing these right. All we lose in going from that diacid to the monoacid is carbon dioxide. So this step is called a decarboxylation. Am I still on the screen? So I'm going to redraw it. I'm going to redraw that diacid and I'll go through the mechanism of the decarboxylation. I'm asking you guys a lot of questions, trying to engage you in class. I'm not trying to make anybody, I'm not trying to put anybody on the spot. But I'll give you a shot at this, all right? The mechanism for this reaction is the same as the mechanism for the diazole. The first step of this mechanism is the diazole reaction. The arrows look the same, all right? Obviously, there's not a diene, it doesn't involve two molecules, but the electron flow is the same. I'll give you a minute to think about that. Actually, before you start that, why would this diacid prefer to look like this than like that? There's a reason. All right, think about that while you totally outsourcing. One of these days, I'll just walk in the room and say, "Thank you." Sit down. What's that? Not quite. Not scared. Depending on how you define it, electron. So why does it prefer? I am thinking why this is. Your arrows are right. No, it's not. It's not that. There is another reason. It can do the process because of the other thing. Maybe think about it. You've actually drawn the arrows two different ways.
This is from my notes.
Oh.
Not from
Oh. There you go.
I wish I figured that out otherwise, but.
All right, anybody got a reason for why it prefers the confirmation? Not sterics.
Electronics, so there's like the O and the H.
There you go. It's a hydrogen bond. Right, that carbonyl oxygen and the OH, it's a hydrogen bond. And it makes, I mean, that's a 6-membered ring, right? 6-membered rings are really stable. So that you, if you have an H, six atoms away from an oxygen, an H and hydrogen bond, you're gonna see a hydrogen bond. All right, so how about the arrows? So Diels-Alder, how many arrows are there? There are 3. So there are gonna be 3 arrows here. And I should have given you the hint that one of the products is carbon dioxide, right? So draw what you get from those 3 arrows, the 3 black arrows. Yeah. And then if you're struggling with that, draw the Lewis structure of carbon dioxide. That's the Lewis structure of carbon dioxide with green. So, you know, humans like to sort of simplify and abbreviate even past the point that it's useful. So in the public discourse about carbon dioxide, you just call it carbon, right? Carbon in the air. There's no, I mean, there used to be, back in the 50s, like we burnt coal everywhere, there was actual carbon floating in the air. Now we mean carbon dioxide. And we tend not to think about carbon dioxide as a chemical when we talk about climate change. But it's important to remember it's chemical. It's got a carbonyl, so it absorbs. Like, why does carbon dioxide absorb IR so well? You guys done some infrared spectroscopy now? Big carbonyl stretch in the IR. 2 funkin' polar carbonyls right there. All right, so how do we get there? That comes from this group. What do we get from the blue thing? We end up with, right? So this bond the double bond becomes a single bond. I should have drawn that out, sorry. Becomes a single bond to the OH. OH bond breaks and makes this pi bond. This carbon-carbon bond breaks and becomes a pi bond. I told you this would make a carboxylic acid. That does not look like a carboxylic acid. What does it look like? Like a diamond. Kind of close. It's an enol. This is the enol of a carboxylic acid. You have a carbon-carbon double bond, single bond to OH, 2 single bonds to OH. So again, we've talked about this a little bit. When you have an enol, that can turn into a carbonyl quite easily. Ask you guys to do that mechanism at home. That's a hint. Enols turn into carbonyls very easily in solution, and the equilibrium favors the carbonyl. Generally, the equilibrium favors the carbonyl by like a trillion times or so. Right? So if you can make this enol, you're gonna, this molecule will almost immediately turn into the carboxylic acid. Okay, so kind of go back. I asked you guys to do a lot of stuff there. If we go back and think about it, what does the malonic acid synthesis do? What it does is it lets us make a carbon-carbon single bond. It lets us make an alkylated enolate. Like this molecule is a molecule we could have made by alkylating an enolate, a simple enolate, simple monocarbonate enolate. But that one reaction, so there's a tendency, and I mean all else being equal, this tendency makes sense. But the tendency is one reaction is better than three reactions. But as you'll find in life, right, a lot of times the shortcut doesn't work. I think there are sayings about this. So if I have one crappy reaction that gives a terrible yield and lots of different products, it might be way better to do three really good reactions. Right? If I've got three reactions that work really well, and if you look at these three, acid-base reaction, just a proton transfer, right? This is 100% conversion in yield. This is going to be a great reaction. Step one of this process is outstanding. Step two is a pretty good nucleophile that's not a terribly strong base doing an SN2. It's not going to be 100% yield, but it will be good. Step three is a hydrolysis and a decarboxylation, and those go really, really well. All right, so the overall process, I should probably draw this on the board. See how far I can push you guys over on the far left, far right of the room. All right, so if I have a dicarbonyl compound, right, where one of them's a carboxylic acid. So if I have a carboxylic acid that's got a beta carbonyl, right? So carboxylic acid carbonyl, alpha carbon, beta carbon's also a carbonyl. If I have a beta carbonyl to a carboxylic acid and I heat it up, I lose CO2 out of the molecule and I get a monocarbonyl. This lets us alkylate the carbon between two carbonyls, as long as one of them is an ester or carboxylic acid derivative, and then heat it up and blow off CO2 and accomplish the same thing as alkylating a single carbonyl. All right, so like I said, chemically speaking, in organic chemistry, this is an important concept. This is the same concept really as protecting groups. Right? Protecting groups always add two steps. I have to add the protecting group, and at the end, I have to take the protecting group off. And you might think, man, that's a lot of work. I don't want to do that. And you're right. I've done synthesis where that's a lot of work, and I don't want to do that. But the alternative is doing the reaction without the protecting group, and it either doesn't work at all or it works really badly, and I end up having to purify a compound. We don't make you guys purify enough compounds in lab to make you scared of purifying things. But it's really easy to set up a reaction. You pour everything together and you let it stir, you go home. The hard part is really pulling out the pure molecule. Yep. No, this decarboxylation reaction always goes from the protonated carboxylic acid, right? You need this there to drive. Yeah. Okay. I think that's enough chapter 21 for a bit. We will come back and talk more. I managed to upload this morning Monday's lecture. It took me a while. I tried twice yesterday thinking it had gone and it had not. And I also added some suggested problems from chapter 21 that you can start looking at. I'm sorry those didn't make it online earlier. We will come back and talk about 21 a little bit more. I want to start chapter 22. A mean. What's the most important chemical reaction people do? What's the most important man-made chemical process? Anybody going to disagree with that? He said nitrogen fixation. It is. We're in a pretty rich country, so I don't know, in a pretty rich country with a lot of farmland, so maybe we'd all be doing all right. But if you go back to the late 19th century, you know, humans had expanded over much of the globe with our, you know, our civilization and our sins. We were running out of food. So for the last half of the 19th century, it was economically feasible for Europeans to sail ships down past South America, up the west coast of South America, fill the ship with bat shit, and sail back to Europe. That made financial sense. All right. And I like to put it that way because, you know, you read it in the textbook, they don't use those words. It's about, you know, global trade and all this highfalutin ideas. I'm like, that's what people did. And they did it to feed themselves, and it worked. Many problems with it. That's a long way to go. And all that guano on those islands, and if you don't know what I'm talking about, read it sometime. It's not going to be on a test. It's an interesting thing, but maybe over Christmas. But all that guano had built up over tens of thousands of years. And in like 20 years, Europeans shipped it all back to Europe. And actually, Americans did the same, but we had a much easier, right? It was easier to sail down there from San Francisco. Anyway, everybody knew that we had a fertilizer problem. And also everybody knew from like the end of the 18th century that fertilizer problem could be solved by taking nitrogen out of the air and turning it into fertilizer. And so chapter 22 is a means. You may, you know, in case you're wondering why I'm talking about all this, right? So this is propylamine. It's a pretty strong base. This is triethylamine. A lot of amine nomenclature is like ethers. It's really easy. By the way, esters don't get named that way. A lot of people on the test name things as like methyl ethyl ester. Can't name an ester that way. Ethers, though, you do. There's an oxygen. It's like two groups bonded to the oxygen. Amines, for a lot of amines, you just name the groups on the nitrogen and then say amine. What makes an amine is the nitrogen, right? The nitrogen is the defining part of this functional group. And the word amine comes from ammonia. And so this is ammonia, and that's definitely one you should know. And ammonia is a base. So you can protonate it, get ammonium. In the same way, these amines can be protonated, and you get the name of the amine. So if you protonate triethylamine, you get triethylammonium. And you'll see, I like to encourage you guys to look at the ingredient list on, you know, products you have in your room. Some of them will have quaternary amine, what we call a quaternary amine. So a quaternary amine is an amine that's got four things on it. So it's either been protonated by an acid or it's been alkylated by a carbon. And ammonium is a really important
component, an abundant component of excrement. And it's part of what fertilizes the field. Like we'd already advanced. I'm talking about the 19th century where, you know, Americans and Europeans largely were sailing to South America to bring back guano. Like that was a significant technological advance upon the earlier method of fertilizing fields, which was how did we fertilize fields before we sailed to South America for guano?
Spreading waste.
Right. So if you were lucky, it was your livestock. Often it was your own. You guys see The Martian? Okay, that was a quick note. Like you're morally opposed to watching The Martian. It's a movie. Like I'm trying to. It's like a 10-year-old movie now. I'm old. Anyway, Matt Damon's trapped on Mars, has to grow potatoes, uses his own waste. Like that was very clever, but it was also how humans have grown. Like for most of human history, that's how we fertilize fields. So we need to get ammonia or ammonium. Really the only place to do that is already living things. So, you know, you plow crops into the fields. Like we've learned a lot. Humans have gotten really good at agriculture. One of the big steps, and this is what I asked, is how to turn, let me just say it's nitrogen. This is 80% of the air around us. Okay. So if you could somehow turn nitrogen into ammonia, which seems like it ought to be easy, right? Then the air itself becomes fertilizer. You don't have to sail to South America and you get rich. You can also make bombs. That's pretty cool too. So it's important. Like, if you want to look at what drives human technological development, everybody always talks about feeding yourself and like building castles. No, killing other people is always like way up on the list. You know, I had a long day yesterday, kind of in a cynical mood. If that's not your game, you don't have to listen to it. You were going to say something.
Isn't that why they came up with those?
So yeah, no, the timeline actually doesn't work on this. You hear a lot that Fritz Haber, who won the Nobel Prize along with Karl Bosch doing this, that they were actually mostly looking for munitions. And that is being overly cynical. So Haber was working on this starting in the late 1900s and succeeded in like 1908, 1909. But he was not the only person working on this. And the reason they were working on this was, yeah, munitions. But it really wasn't. Mostly what they were working on is scientific glory. So the other reason scientists do what they do is to beat other scientists, right? If you can be the first person to do something, the first person to discover something, the first person to build something, one, you get like credit, you get to strut about. You also usually get a lot of money. And both Haber and Bosch made a pile of money off this stuff. But it was an interesting scientific problem. So what would you add, just thinking about the chemistry you guys know now, what would you add into to make NH3? Not an oxidant. The other.
Oh, reduce.
What actual element do I have to add? You have to add hydrogen. So if you can add hydrogen, first thing, right? If you hydrogenate an alkyne, a carbon-carbon triple bond, you get an alkene, carbon-carbon double bond, right? And then if you hydrogenate that, you get hydrazine. And here wound up being the cool thing. The thing that you had to figure out was this step. Because once you get to here, this is really easy. Hydrogen gas and diimide or hydrazine go to ammonia like easy. The hard part was this. Nitrogen gas, you guys may have noticed, is really inert. Right? That's why there's so much of it.
everywhere. There was a lot there's a lot on Earth. There's a lot around Jupiter, Saturn. Like there's a bunch of nitrogen because it forms in whatever, nebula it gets formed in. It just doesn't do anything. Like think about all the chemistry going on Earth. I mean, 20% of the air is oxygen, which is this powerful oxidizer, and nitrogen just sits there and kind of looks at it. Doesn't do anything. Not many molecules just sit and look at oxygen and don't do anything. All right, so this step you got to figure out. And it's a really cool story and beyond the scope of this class, right? Figuring out what catalyst drives this. This is the same old problem. You've got two different molecules. You got to turn them into one molecule. Entropically, that's not favorable. Enthalpically, though, we're breaking a pi bond. We're making sigma bonds. Delta H says this should go. Delta S keeps it from going. So you got to find the right conditions. This was what the search, of course, like we all know, you guys right now, and whatever you think about your chemical abilities, whatever I think about your chemical abilities, promise you, you guys know more thermodynamics right now than anyone knew in 1890, including all these people that eventually did this, right? So if you could time travel, which is a whole other problem, if you could time travel back to like 1870, you'd be a titan. I mean, if you could time travel back to 1870, presumably you're already a titan, right? So there's a whole lot of there probably are other ways to make money than doing this, but that's what I would do. All right, so what they end up finding out, what they end up doing, hydrogen gas, right? 3 equivalents of hydrogen and an osmium catalyst. Problem with osmium is, 1, it's super toxic. That's not really a problem. 2, it's very rare. It's extremely expensive. And so people had done this a little bit. Nobody ever done it. So they wound up using this mineral called magnetite, which is basically iron with a little bit of osmium in it. Then they work out an engineering way to keep the reaction at the right temperature and the right pressure. Anyway, like I said, Haber figures this out. A company called BASF. Has anybody heard of them? BASF? Google BASF sometime. Not right now. They did okay in this deal. So they bought the rights, paid Haber a fortune. 1909, it's not a history class, so I won't put you on the spot, but World War I starts like a few years later. So this does get published. The Germans made a lot of mistakes in the 20th century. The 2 chemical mistakes were that they discovered this. So the Germans in the 19th century basically ruled chemistry, right? Up until my lifetime, graduate students in science had to take German so they could read the chemical literature. Keep stuff close to yourself. So they discover this a few years before World War I starts, right? So the English and the French and the Americans all know about this. They do kind of the same thing in 2 respects with World War II. They discover antibiotics and fission a few years before World War II. Like they discover any of those things like as the war is starting, so they don't publish it. Maybe things go different. I'm glad they didn't. But like imagine, well, don't imagine, it sucks. So anyway, this is a really important chemical reaction to feed your family, to and explosives are important other than killing people. Like if you want to drive a highway through a mountain range, you need explosives. None of that stuff is what we're going to talk about. My question is, why does this not give us all the amines we need? All right, you would think at this point, we've got ammonia, now I can just do this. I'm going to get an amine. Right? SN2 reaction that I've been talking about all morning, afternoon. Ammonia plus methyl bromide, we get methylamine. So this is what I want you to think about over the next few days. This is not a good reaction. Why is it not a good reaction, and what can we do about it?
All right, like I said, none of that history stuff is gonna be on the test, but it's stuff I hope you guys will think about. We talk about, you know, a liberal arts education. You are supposed to connect this class to like your history classes and politics classes and philosophy classes. Like, why is it bad to blow people up? That sort of thing. By the way, Haber, just the last thing I'll say, some of you know I've done 2 study abroad programs to Chile. Haber discovering this basically wiped Chile out. All right, Chile was a fairly significant economic power because they had all this bat guano. And actually then there was also a lot of sodium nitrate that just lay in the Atacama Desert. The Europeans and the Americans, as we do, went down, shoveled it all into boats, paid a few people a lot of money, and then took it all. Haber discovers this, and all of a sudden you don't need to like go sail to South America to get bat guano. You can just make it from air. So like all this stuff that we're talking about does connect to the wider world, is where I was trying to go with that. I will see some of you in lab. Who had lab yesterday? Anybody? Did you like lab yesterday? Be enthusiastic about like cool colors. I didn't get to azo dye chemistry in here. The chemistry you guys are going to do this week in lab, we will talk about probably on today's Wednesday. It's like Monday. I'll talk about that on Monday. So next week we'll talk about the chemistry you're doing. It is really pretty. So if you're in today's lab or when you take lab this week, enjoy it. All right, that's it. That's all I have.